So, in the previous video, we gave some general definitions of difference equations, and we specialized to linear difference equations. However, we stated everything pretty abstractly and didn't really give many concrete examples or intuition. Now, if that already made sense to you, then, well, you may not need to watch this video. However, if things aren't crystal clear, hopefully we'll be able to clear some things up now. Let's go back through the lecture step by step, and I should again first mention the textbooks that this course will be following, including especially Linda Allen's An Introduction to Mathematical Biology. That is the backbone of this course, and the definition numbers will correspond to the textbook, so you can follow along in the textbook if you have a copy in front of you. So now let's go to definition 1.1. We defined a difference equation of order k pretty generally. We said that it's just some arbitrary function of the state variables that, and setting that function to 0. An arbitrary function of both the state variables and our time variable, which is set to 0. For example, let's write out a concrete example of some function that might fit that. So let's give an example here. Let's say we have f of x sub t plus k, x sub t plus k minus 1, so on, all the way to x sub t, and t, of course. And let's say that let's call this function f, and say that it is equal to sine of x sub t plus k, x sub t plus k, plus t times x sub t plus k minus 1 times x sub t. So now, that's clearly a function of the correct form. It depends on some subset of the variables x sub t plus k through x sub t and t. And if we now set this equal to 0, let's see, if we set this equal to 0, then this is now a difference equation of order k. But, of course, that's not all we talked about. There are several other conditions that make up part of this definition. The first one here is that t comes from the natural numbers, so 0, 1, 2, 3, so the counting numbers. That isn't so surprising because we're talking about difference equations, and so that corresponds to the discreteness of time. You can think of this as the time interval between 0 and 1. So we basically normalized according to however long our time interval is, and we've set that equal to 1, and so then we just have to count up. Some of you may find it easier to think of it in terms of 0 years, or 1 year after the start point, or 2 years after the start point. But the unit doesn't really matter for what we're trying to do, since we're trying to model it in an abstract manner. Also, I have here that we are working over the real numbers. That's just the technical condition. Things get a lot harder when you, for example, work over the complex numbers, and we're not going to deal with that so much in biology, since most of our quantities are real. And we have here the Stotz condition, that f must depend on both x sub t plus k and x sub t. Now, this condition is actually only necessary in order to say that something is of order k. For example, if we were to modify this equation slightly, and say we replace this x sub t with, say we place this x sub t here, with x sub, let me move this equals 0 over to the slide a bit. Say we replaced that with x sub t plus k minus 2. Well then, strictly speaking, this is still a function of x sub t plus k through x sub t and t, but it no longer actually depends on x sub t. And in fact, if we look at this a bit more closely, this modified equation is only of order 2. And so the reason we had this additional technical condition is just basically so that the difference equation is actually of the order of order k. Okay, so now we've parsed that definition. Let's go on a little bit and talk a little bit about some of the other definitions. So we define the difference equation as autonomous if f does not explicitly depend on x. So again, even though our function f here can depend on t or any of our state variables x sub t plus k through x sub t, it doesn't necessarily have to. And indeed, we can think about writing another example. Let me do that in purple here. So let's suppose we had another example here, which would be f of x sub t plus k, x sub t plus k minus 1, all the way down to x sub t and t. So if that happened to be equal to, say, sine of x sub t plus k plus, let's just drop the t and replace that with a 1. So since we're multiplying by the identity, that doesn't show up. So let's say that's x sub t plus k minus 1 times x sub t. And let's set that equal to 0. Well then, this example here, because it doesn't have an explicit dependence on t, it still might have a dependence on t through the state variables, and indeed the state variables are evolving with time. But what this means is that the t value doesn't enter into our equation directly, and so if you were to start at time 0 versus starting at time 10 with the same initial value of your state variable x, you'd end up getting the same dynamics just shifted over. So that's what it means for something to be autonomous. So we've dropped the t here. T has been dropped. And of course, so we just call it non-autonomous otherwise. Okay, so now those are all pretty general forms of difference equations. And it turns out that solving a completely general difference equation, even if it's autonomous or of some particular order, a known order, is actually quite hard. And so often we tend to focus more on a commonly encountered form of a difference equation where we're setting x sub t plus k to here, where we have x sub t plus k as a term in and of itself, and we're saying that plus the sum of some set of functions ai, which can depend on any of the other state variables x sub t plus k minus 1 through x sub t, or the time variable t, and then we multiply those coefficient functions by a copy of the various other state variables, and we're setting that equal to b sub t, where b sub t is an element of R. So that depends only on time and doesn't depend on any of the state variables. Now, you can't always easily rewrite an equation in this form, but if you can rewrite an equation in this form, then it becomes a lot easier to understand and interpret. One obvious initial thing that you might notice is that when you have written an equation in this form, the order is k if a sub k is not equal to 0. And this is because, give me a moment. Anyway, as I was saying, the order is k if a sub k is not equal to 0. And this is pretty easy to see because if we were to write this out explicitly, then what that means is we have some function x sub t plus k plus the summation, and let's go only up to k minus 1 here, and let's break out the last term. X sub t, and x sub t plus k minus I, and plus, of course, we're breaking this term out, so this is a sub k, so it's the kth one of these coefficient functions, and of course it can be a function of all the state variables, x sub t, and here we have just x sub t. And let's go ahead and move the b sub t over onto the left-hand side, just so we have it in more standard form. And we're setting that equal to 0. Well, if you look at this function, so long as this a sub k term is not equal to 0, this entire thing is obviously going to explicitly depend on both x sub t plus k and x sub t. So one of the nice things about an equation in a difference equation in this form is you can just read off the order by looking at the coefficient of a sub k. The other nice thing is once you have this form, well, you can, if you rearrange this equation slightly, well, let's do that now, you can of course rearrange this equation as x sub t plus k is equal to some summation of I sub 1 through k. I'm going back to the original summation here, so I'm collapsing it back in, of x sub t plus k minus 1 all the way through x sub t as well as t times x sub t plus k minus I minus b sub t plus b sub t, since we're going to move everything over to the right-hand side. So now this form of the difference equation gives us an explicit formula for allowing us to compute the next step in the state variables. So long as we know the state variable is x sub t through x sub t, state variable is x sub t through x sub t plus k minus 1, we can compute x sub t plus k. And so this is a much more useful form for actually doing computations. Because up here, let's see, where were we? Up here in this general form, where there's this sort of functional form of the difference equation, it could be rather difficult to figure out what x sub t plus k actually is based on the lower order terms, because you have to solve for some complicated equation. Here you don't have to solve, you just plug stuff in and compute. Okay, so now we've done that, we've rewritten our difference equation in the standard form. It turns out that very often even that standard form is quite complicated, and we don't always have good methods for solving difference equations, even of that generality. Though often we can. It will depend on what exactly the coefficient functions are. One easy form, so-called easy form of the coefficient function, so these a sub I of t's, is if those things are only dependent on t. If those, unlike this general form where they can be dependent on any of the state variables except for x sub t plus k, if they happen to be dependent only on time, they don't have any dependence on the state variables, then that is actually super helpful, because that is what we call linear. So the state variables only come into play in this linear summation form. So they only come into play once as a part of the summation and are multiplied linearly with a particular coefficient. And so when that's the case, it turns out we actually have a lot of good methods for solving the difference equations. And so we call that linear. And otherwise we call it nonlinear. Now, we will still be addressing nonlinear equations, but in chapters 1 and 2, we'll be focused primarily on linear difference equations, and then, in chapter 1, we'll be focused on linear difference equations, and chapter 2, we'll move on to some subsets of nonlinear equations and some methods we have for understanding those. Though, although nonlinear equations are a lot more general, they're also just harder to solve, as you might expect. One other useful classification is homogeneous versus non-homogeneous, which you should recall from your differential equations classes. So this is the same sort of idea. If a difference equation is linear, and b sub t, this term on the right-hand side, this b sub t term is equal to 0 for all t in the natural numbers, then it is homogeneous. Otherwise, we call it non-homogeneous. And for the purposes of this class, we'll only call something non-homogeneous or homogeneous if it is linear. We're not going to deal with whether or not you can even apply that term to a nonlinear difference equation. So what might be an example of that? Well, the obvious thing is if you go back up to our autonomous equation up here, this actually is an example of a homogeneous function. Actually, it is not an example of a homogeneous function because it's not linear. Let me find a better example down here. Actually, we don't have any good examples yet, so let me write down an example of a homogeneous function. So let's pick an easy one for this next example. So if we have something like x sub t plus 1 is equal to at x sub t plus bt squared x sub t minus 1. So this is example 1.1 in the textbook, or almost example 1.1 in the textbook. And if we add plus sine of t, then this is example 1.1 in the textbook. Well, now, the question is this homogeneous? Well, let's rewrite this. First, we need to check if it's linear. And so we can rewrite this. So here, this is a summation. This term here, let's see. Let's say that a and b are constants. So this term here is the term in front of, is only dependent on t. So this is some, let's call it a1 of t. And this term here, let's call it a2 of t. And so this is a linear equation. This term here, let's call it b sub t. This is a linear equation, and so we can ask the question of if it's homogeneous or not. Unfortunately, as you'll notice, we have b sub t is equal to sine of t, which is not equal to 0, and so therefore this is non-homogeneous. Non-homogeneous. But of course, if we take out the sine of t, so if we take the sine of t variable here, so if we cross this out, then all of a sudden the remaining stuff is homogeneous. And a number of methods that we'll be using to solve these difference equations, especially solve linear difference equations, will depend on the fact that we can will depend on first solving the homogeneous version of a linear difference equation, and then using that to find a general solution, and then adding that to a particular solution of your non-homogeneous equation, and getting a general solution for the non-homogeneous problem. You'll recognize this as the method of undetermined coefficients from your differential equations class, and there is a perfect analog of the method of undetermined coefficients for the difference equations as well. Okay, so let's see. That's covered some of the basic classifications of difference equations. Now let's go on and talk a little bit about systems of first-order difference equations. So now here, in the previous examples, we only had a single difference equation. What happens if you have several different state variables? So maybe x1, x2, and x3 are all state variables. There is actually a slight problem here where we're slightly abusing notation. So hopefully this won't confuse you too badly. Basically, we want to index our state variables, and of course we want to have them to have a t-dependence. So here, we're doing exactly that. Where previously, okay, let me add this in since it might be somewhat confusing. Previously, we had x sub 1, x sub 2, x sub previously, x sub 3, so on, were our state variables, right? And we had our some evolution. So x1 goes to x2 as time goes on, goes to x3. So basically, this is x sub t. Now here, we've changed the notation slightly. The first thing is, well, let's see. Now, in this definition, we have that we have something like x1 of t as a function. So this is something like, let's not use that arrow. Let's say this is going to be x1 of 1 to x1 of 2, x1 of 3, and so on, because it's x1 of t. And so this is slightly confusing because instead of using the subscript to place the t dependence, we're using the subscript as just a separate index. And then we can similarly have some other set of state variables, x2 of t, which is going to have the same sort of thing. It's going to depend on time, x2 of 3, and so on, x2 of t, and of course that evolves to that as time goes on. I apologize for the slightly confusing notation, but that is what our textbook uses, and you'll just have to get used to it. Another way of thinking about it, which might make life a little bit easier if you only have a very few, if you only have, say, 2 first-order difference equations, you might have you can use different letters for it, and sometimes that can be evocative. So for example, here, instead of writing x1 of t and x2 of t, maybe you'd write just x of t and y of t, in which case you have x of 1, x of 2, x of 3, and so on, x of t, and this is y of 1, y of 2, y of 3, and so on. But because we don't know how many difference equations we're going to have, and each of the sets of each of the first-order difference equations can have a separate variable that it's defining, we need to have this arbitrary index notation. And so we're going to be using this a lot. Okay, so now we've cleared up that notational issue, we can rewrite all of our, we can redefine each of our classifications for systems of linear first-order difference equations as well. Actually, did I require that? A system? Yeah, so these are first order. And so if we're going to write them in our nicer format, of course, because that's what just a lot easier to work with. So now, if this statement here, if x sub I of t plus 1, remember, this is just saying that in our ith difference equation, we're going to set this, and we have each bunch of different difference equations. Let's see if I can. Okay, so that gave us a little bit of space, but I lost my k. Come down, k. So if we were to write that out, let's just take the case of k is equal to 3. So we have system of three first order equations. Then we have that is explicitly for k equal to 3. If we write that out, that's going to be x sub 1 of t plus 1 is equal to f sub 1. So we have some function. We're going to index it with the 1 of x sub 1 of t through x sub k of t. Oh, it looks like I have gotten ahead of myself. Yeah, but in this case, we're going to stick with the k equals 3 example. And you note that here we don't have any explicit t dependence. So here, that's going to be for I equal to 1. And let's say we have the same for I equal to 2. Actually, instead of having k, we can just write them out explicitly. x2 of t, x3 of t. This is equal to f2 of x1 of t, x2 of t, x3 of t. And let's give ourselves a little bit more space. This here is x3 of t plus 1 is equal to f3 of x1 of t, x2 of t, x3 of t. And so we're going to call this autonomous because we don't have any explicit t dependence on it. Now, of course, if we were to add in a t dependence here, so if we were to add in the t dependence, then all of a sudden that makes it non-autonomous again. So it's the same principle as with just a single difference equation. If there's an explicit t dependence, then it's non-autonomous. If there is no explicit t dependence in any of the things, so it's actually still non-autonomous, even if only one of them has an explicit t dependence. So even if you were to do this, that would make it non-autonomous. Okay, so now that we've gotten that far, we have similar ideas of linearity. So in this particular case, we are wanting to break it up into a summation where we multiply by each of our variables, each of our state variables exactly once. So that is what we have here. And if we can write it in that form where we multiply by each of our state variables once, then it's linear. If we can't, then it's nonlinear. So let's give a concrete example of that. So let's just do a system of two equations to make life a little bit easier. So let's say we have, and I'll use the x and y notation just so that you guys see several different ways of writing these equations. So if, let's say we have x of t plus 1 is equal to, let's say, t squared x of t plus 5y of t plus 5. And let's say we have another one here. So this is our system. Y of t plus 1 is going to be equal to, let's say, sine of t times x of t plus t minus 1 times y of t. And let's say that's plus t squared. So this system here is linear, because each of our state variables here only appears once and is not multiplied by any of the other state variables, and it's only multiplied by some function of the t variable. And so this particular example is non-homogeneous because we have a b sub t term that's not equal to 0. If we set those equal to 0, then it becomes homogeneous. Okay, let's move on. And now we get to the punchline. So now that we also gave a definition in 1.4 for what a solution to a difference equation is. And now this is just a long-winded way of saying that a solution to a difference equation is a function that if you plug it in to the difference equations, makes all of them true. So let's give an example of a simple one of these. So let's suppose we have a super simple difference equation, which will show up again and again and again. Let's say that we have example I think this is one of the examples in the book. Let me check quickly. Yeah, this is 1.4. Well, it's not quite 1.4, but it's quite closely related to 1.4, so we'll use this. So let's say that x sub t plus 1 is equal to ax sub t. So you may see basically this in the example 1.4, this is talking about basically an exponential growth of a population or exponential decrease of a population. So let's just give a complicated example. Suppose these are individuals in a population at a particular generation time. Generation number, let's say. So for example, if you recall from our pre-lecture, our preface, where we talked about cicadas that have really discrete generations, maybe x sub naught is the initial generation of cicadas in the total number len, and x sub 1 is the next generation, how many cicadas are in that one, and so on. And maybe they reproduce exponentially because the cicadas live in a land of plenty, and there are plenty of resources around, so they don't have to worry about any sort of carrying capacity or other fancy stuff like that. So suppose we have this set of this particular difference equation. So now, what is a solution to this? Well, there are a couple different possibilities, and let's take a look at it. So if x sub t plus 1 is equal to a times a sub t, where let's say a is a constant, well, then we start with x naught, and we have x sub 1 is equal to ax naught, x sub 2 is equal to a squared x naught, and so on. So this is actually fairly easy to solve, and we end up with x sub t plus 1 is equal to a to the t plus 1 times x naught, or actually it's slightly nicer if you just write x sub t is equal to a to the t x naught. And so, of course, x naught could be arbitrary, but let's just say that, x naught is, just a moment, let's see. So say that x naught is equal to 1, just to make life easy. Well, in that case, we have that a function x sub t, which goes from the natural numbers to r, defined by x sub t is equal to a to the t times x naught, solves the difference equation x sub t plus 1 is equal to axt. And this is because the t term here goes from, we should probably say x. And then, of course, at any particular time, x sub t, where t is taken from the natural numbers, we have some particular real number of the number of individuals at that particular time step. And so this is a solution to this simple difference equation. And, of course, a solution to a system of difference equations is also just a function from the natural numbers and the index set, 1 through k, to r, that makes the difference equations true. So now, often we'll write this in this vector notation here, where we specify each of the different functions corresponding to the index set for the solution. But in this particular case, here, this is just the index set, and this here is time. And we won't give an explicit example of this here, but we will in the problem sets, that we'll be working through in class. I think that about ends the elongated explanation of linear difference equations. In the next video, we'll be talking about some methods for solving first-order equations. So I'll see you there.